All right, so I want to look at the back page of 2D. Um, and there are a few theorems here, or a couple theorems. One of them is called the fundamental theorem of algebra, and it says if you have a polynomial with degree n, then it has n complex zeros. And complex, when I say complex, that includes real numbers and non-real numbers. So like 4 is real, 4 plus I is non-real, but they're both called complex numbers. This would just be 4 plus 0I. Okay? So they all count. They all count. And some of the zeros might be repeated. So, like, let's say the polynomial you're looking at is x minus 4 squared times x minus 1. That's really an x cubed polynomial, right? So the theorem says that it's going to have, since it's a polynomial of degree 3, it's going to have 3 complex zeros, real and non-real. So if you look at this one gives you x equals 4. This one gives you x equals 1. But x equals 4 happens twice, right? Because it's x minus 4 times x minus 4. I could also write it this way, right? So x minus 4 is a repeated 0. You would call it a 0 with multiplicity 2. And x equals 1 is a 0 of multiplicity 1. So still you get 3 zeros. In this case, they're all real, but one of them's repeated twice. And then the linear factorization theorem down here says if you have a polynomial with degree bigger than 0, then the polynomial has n linear factors. So it means you can basically break it up into, you throw that leading coefficient in front, and then you can break it all up into terms like this: x minus some number, x minus some other number, x minus some other number. These might be real, or they might be non-real. Non-real terms have the form a plus bi, just so you remember. So like a term like this could be x minus like 1 plus 2i. It could look like that, just so you realize. That's actually still, they use z to refer to complex numbers, real or not real. So, okay. And again, since these can repeat up here, these might repeat down here. Okay. Um, so then they're following these statements here are all saying the same thing. X equals k as a root means that when you plug in k, you get f of x equals 0. That's the same thing as saying it's a solution. Okay, so this implies f of k equals 0. And we've been referring to this then as a 0 of the function, which is what 2 says. And if it's a 0 of the function, then you know that you can write the function as x minus k times something else with no remainder, because the remainder is 0. Remember, the remainder theorem says here that if f of k equals 0, the remainder when you plug in k is 0. Okay, so those things all say the same thing. Really, the rest of this page is essentially some multiplication practice, because it gets a little bit tricky at times. And I just want to review a little bit of it. So write the polynomial in standard form and identify the zeros. Okay, so one thing here to note, notice how it says minus 2i and plus 2i. Right here it's going to say x minus I root 2, x plus I root 2. Down here there's a minus I, there's a plus I. They always come in those conjugate pairs. We're not going to prove it. I don't think we're going to prove it, but they always do. They always do. We could prove it. It's not that bad. It just uses quadratic formula. Okay. So let's multiply this out. If we multiply the first two terms, we get x squared. If we multiply the outer terms, we get 2ix, but then I'm going to get negative 2xi. So those are going to cancel. And then the last two terms here, negative 4i squared. So minus 4i squared. And remember, I squared, I equals, well, just I really, which is square root of negative 1. And then I squared is going to be this thing squared, so negative 1. And that's pretty much all we're going to need, but I'll write here. I cubed is going to be negative I. And I to the fourth is going to be 1. Those are things you should remember. Okay, but really, for the most part, I think that's all we're ever going to encounter. So this is going to be x squared minus 4 times negative 1, so x squared plus 4. Okay. In the next one, we've got one with a real root here, and then two imaginary roots. And so what I'm going to do, I would suggest you guys do the same thing. Multiply these two together first, because the fact that they're conjugates means you're going to get rid of some stuff in the middle that would normally be there. So when I multiply this out, I'm going to get first x minus 5, and then I'll get x squared. When I do x times x, I'll kind of motion at it. X times x, so x squared. And then this term, ix root 2 and xi root 2, one of them's positive, one of them's negative, so they're going to cancel. And then I'm just left with the negative I root 2 times the positive I root 2. So it's going to be minus I squared, and then root 2 times root 2 is 2. So then that's going to turn into x minus 5, we'll simplify, x minus 5, and then x squared plus 2. So now we can multiply this out. And if I multiply the first terms, I get x cubed. If I multiply the inner terms, let's say, I'll get minus 5x squared. If I multiply the outer terms, I'll get plus 2. By the last terms, I'll get minus 10. So there's that function. And then for the last one, we've got 4 terms to multiply here. So I'm going to multiply these two terms together, and then I'll also multiply these two terms together. So the first two terms together, x squared minus 6x plus 9. The last two terms multiplied together are going to give me x squared, and then the ix and the negative ix will cancel. And then I've got minus I squared. So it's x squared minus I squared. So then this will become x squared minus 6x plus 9 times x squared plus 1. Now when I multiply this out, the way that I tend to do it is I look for powers, things that will give me powers first. So if I look at the powers, the biggest power we're going to get is x to the 4th. Okay, so x to the 4th here. Then the next biggest term I could get is an x cubed term. So I look for ways that I could get x cubed, and the only way I could get x cubed is this x squared has nothing to multiply over here with. But this x squared could multiply with that. So I'm going to get a total of negative 6x cubed. The next thing that I'm going to look for is going to be x squared terms. So I could get x squared terms by multiplying this x squared with that one. So that's 1x squared. And I could get it by multiplying this 9 with this x squared. So that's 9 more x squared. Then there's nothing to multiply this x with over here to get x squared. So let me erase these things so that they're out of the way. So the total number of x squareds that I could get here are going to be 10x squareds. And then let's see, x terms. So x terms I could get. I've got an x term here, and I can multiply it by that constant. So that's going to be minus 6x. And then that's the only way I could get x terms, so minus 6x. And then the last term is going to be the constants, so I got to multiply 9 times 1, so plus 9. Okay. If you like working it out in the longer ways where you do x squared times this x squared times this one, negative 6x times this x squared, negative 6x times this one, 9 times x squared, 9 times 1, and adding them all up, add up all the like terms, that's fine. Yeah, you can stay away. The only reason I'm doing it this way is because later on there may be even some longer things that we need to work out, and this sort of makes it shorter in a sense. Okay. The very last one says find all the zeros of f, then give the complete linear factorization. The linear factorization is the same as this thing up here. Linear factorization, you can write it as a coefficient in front with just a bunch of linear factors after it. So let's come back down here. Whoops, sorry. Now this one is going to factor by hand. So if we factor by hand, f of x equals, and then you can do that trick where you do grouping. So I'm going to look at the first two terms, and then I'm going to look at the last two terms. So first two terms, if I factor out an x squared, I'm going to get x minus 3. And the last two terms, I'm just going to factor out a positive 1, and I'm going to get x minus 3 again. So this turns into x squared plus 1 times x minus 3. Now at this point, I need to give linear factorizations of f. This one's a quadratic, not a linear. So, but it does factor if I start considering I. So this turns into x plus I, x minus I. This term right here, so I'll highlight this. This term turns into this term, and then I still have that x minus 3 after it. Whoa. Let's go with the thin one. And if you wanted to double check it, you know, you could do x squared, the ix and the xi cancel, and you're left with minus I squared. Well, remember that's -1, so this turns into x squared plus 1. And that's sort of the point as to why we did this stuff up here, right? X minus I, x plus I turns into x squared plus 1. If we go up a little bit higher, there were some other examples too. This one turns into x squared plus root 2 squared, right there. Right? If we go up a little higher, this one turns into x squared plus 2 squared. Right? So you can start to see the patterns there. Anyhow, this, and so all the zeros of f, the zeros are going to be plus or minus I and 3. Notice there are 3 total zeros, and it was a cubic function, right? That just because there are 3 total zeros, some of them might be repeated, you know, but in this case, they're all unique. They're all different.